So today we have a great pleasure to invite Professor Hsiang-Kuang Chang from Tsinghua University. And Hsiang-Kuang got a PhD from University of Bonn. And he went to a very short time of the postdoctoral fellowship at the Los Alamos National Lab at the US. Then he returned to Tsinghua as an assistant professor. He has now been to serve like the chair of the Astronomy Institute and also the department vice chair of physics. Both. And he has been served many committee members over the Taiwan different community. And he is an expert in the high energy astrophysics and specializes building some normal instrumentation for detecting very energetic photons like gamma ray. And today he will be talking about MeV astronomy and instrumentation developed in Taiwan. So let's welcome Hsiang-Kuang.
Good afternoon, everyone. So thank you for the invitation and introduction. So it's my pleasure to be here and see many friends here. And today I will talk about MeV Astronomy Instrumentation development in Taiwan. MeV, as Ken mentioned, very high energy, but actually in gamma ray astronomy, this is low energy gamma ray. Okay, so we have low energy gamma ray. Okay, and the background picture is a satellite. And I took this picture from NSPO's website, and I believe this is not the real future satellite because the cover would not be like this. But somehow NSPO put this picture there, so I took it to use. And at the end of my talk, I will tell you, indeed, something like this will be our bus. We will have a payload to fly on NSPO's satellite Formosat 8 in hopefully 4 years. Okay, good. So I'm Hsiang-Kuang from National Tsinghua University. Okay, good. So I'll talk about MeV. So as you know, in astronomical observations, we observe photons, and now, of course, neutrinos, gravitational waves, and cosmic rays are also the messengers that astronomers want to measure. But today I will talk about electromagnetic waves. And across electromagnetic waves, because of different technology and so on, blah, blah, blah. And you probably all know that only optical and radio, and actually some TeV photons will interact with our atmosphere to make some fluorescent light or charcoal light, so that optical telescopes actually are also used for detecting TeV photons underground. Okay. Besides these bands, we need to go to outer space because of the Earth's atmosphere. So you can see there are a lot of space telescopes from radio infrared optical to this is Chandra and this is New Star. They work on X-ray band, half X-ray band, and this is integral. This is Fermi. So this is about GV band. And what we are working on is MeV band, which is probably here, MeV band. All right. So to begin with, in MeV band, of course, there are a lot of things to investigate. And here I try to use only one slide to summarize the rich science in one slide. Okay. And so let's do it this way. And I believe this is not a complete list, but let's do it this way. We can consider line emission, and continuous emission, and also polarization. Yeah. So for line emission, then one very important issue is the 51100 kV line from our galactic center. Okay, and as you can see, there's a whole sky map here. This is 111 kV map of the whole sky, and you see there's a bright source at our galactic center. So what's going on there? And you know this line, if I do this talk in high school or in undergraduate program, I will ask the audience, do you know what's special for this number? And very often, no one knows. Very often, no one knows. But I dare not ask you here. So let me skip this question. Okay. Then, of course, with this line, then we know there are a lot of positrons there. So what's the origin of the positrons? That's one issue. Okay. Particle physics is preferred to say, oh, that's a dark matter decay, blah blah blah. That's nice. Yeah, but astrophysicists then argue for possible origin from supernova events, from binary, X-ray binary, this kind of thing. So there are different theories, different models. The important thing is to have more confident measurement to see the spatial distribution and also to see the spectral type, spectral shape, the line shape. Okay, anyway, this map is taken from a paper published in 2008. In 2005, there was a similar paper which showed a very symmetric distribution. In 2008, with some more data, MEV data, then the author of this paper claimed that they found this asymmetric distribution. So they claim this is related to low mass X-ray boundary because the distribution of low mass X-ray boundary in the disk is similar to this. But then later on in 2010 and 2015 and recently 2020, new observations actually indicate that there's no evidence to say, to argue for this asymmetry. There's no evidence. But basically, we still see a bright source here, and then there might be some disk emission. So what's the origin of those positrons? We don't know. Okay, so that's a very, very good question for MeV astronomy. And also, as you know, there are many lines. Some of my background is white, so this flashlight doesn't really work. Okay, that's fine, that's fine. There are many lines, nuclear lines. They are all in MeV range. So we, through this kind of line emission observation, we can study nuclear synthesis. We can study supernova event. We can also study interstellar medium, because interstellar medium, there are, for example, carbon and oxygen and so on, and high energy cosmic ray, basically protons, heat oxygen, heat carbon. They will excite those nuclei, and therefore they will decay and emit lines. So one can study all these things. So, and also continuous emission. Many systems, in particular compact object systems, have emission, high energy emission, continuous emission. So for example, systems containing neutron stars, radio pulsars, some gamma ray pulsars, and X-ray binaries also. And X-ray binaries may contain neutron stars or black holes. And also AGN, from radio to GeV, TeV emission. So AGN is also a very important source for MEV photons. And of course, gamma ray bursts, they peak in this energy range. The energy peak of GRBs is roughly between 300 keV and 500 keV. So it's within this MEV range. Okay, so these are important. And polarization. Later I will show you that to detect MEV photons, very often one use Compton scattering. And with Compton scattering, then, because the cross-section of Compton scattering is polarization dependent, therefore, it's possible for one to measure polarization with MEV instruments. And if I can measure polarization, then we will have very powerful knowledge or tool to distinguish different theoretical models for different systems. And up to now, basically pulsars and pulsar wind nebulae, and also some black hole binaries and GRBs have photons, MeV photons with polarization measure. Okay. All right. So I hope this is good enough for science. Then I will go to instrumentation. All right. Oh, some remark, because these lines then they are related to a supernova, particular 1A, and there's some implication on cosmology, and also GRB. GRB is EM counterparts to gravitational wave events, short GRBs. Okay. Yep. All right. Therefore, today I will talk about 3 projects, and COSI, COMPOL, and GTM. All right, so I will go through these 3. Hopefully, I have enough time. Yeah. Okay. And I will have one summary slide for each project. For example, COSI, the Compton Spectrometer and Imager. This project, the current status. This project was selected this year by NASA SMEX program. SMEX program is a small satellite. Small means several hundred kilograms. Okay, small satellite. Yeah. Well, NASA classified SMEX and MeDEX by funding level, not really by weight. And SMEX, I think the cap is roughly $200 million for one project. It does not include launcher, of course. So $200 million. So COSI was selected by NASA, but for phase study. So there are 2 teams now under this round of SMEX, and next year there will be a down selection. The other team is a payload for detecting UV, some stellar flare with a strong UV emission. They want to study whether that kind of stellar flare affects the exoplanet, how they affect exoplanet. That's another mission. So I'm not sure next year whether COSI will be selected again or not. Yeah. If it is selected again next year, then it will be launched in 2025. Then we will have a general purpose. COSI is a general purpose MEV mission. General purpose means the previous slide, all those science. COSI can do all those sciences. Okay. All right, so that's the current status. And COSI actually is a project for next generation Compton telescope. Later you will see some more details. And the PI now is John Tongsick in UC Berkeley. And Tsinghua University with some other institutions in Taiwan actually participate in this long-term effort since 2006. So it's more than 10 years, now it's 40 years. All right. So basically, with this figure, I just want to remind you that this is photon energy. And this is atomic number of the material of your detector. And this part means Compton effect dominates. And for low energy ones, absorption dominates. For high energy one, pair production. Pair is electron and positron pair. Positron pair production dominates. So you can see if we are interested in MEV, this is 1 MeV, 10 MeV, 100 keV. If we are interested in this range, then Compton scattering is the major channel of the photon and matter interaction. So MEV telescope should use this working principle, Compton scattering. Okay. All right. Therefore, COSI is the next generation Compton telescope. Compton telescope is a telescope which exploits Compton scattering as the working principle. Okay. So the last generation is something like this. This is COMTEL on board CGRO. So this is a huge mission in the last century, okay, in 1990s. For this COMTEL, the idea is that there are two layers of material. They are both scintillators, different kind of material. An incoming photon, MeV photon, hit the material here, scattered by the material, by the electron in that material, and then go to the next layer. And very likely, because the energy gets lower, so very likely they will be absorbed by the lower layer. So by measuring the location, and the energy of the recoiled electron, you have energy. Therefore, you can reconstruct the incoming direction of the photon, and you can also estimate the energy of the incoming photon. Therefore, that's your astronomical observation. You have direction, you have energy. Time is not really an issue. Okay, so that's basically the principle. Because one use Compton scattering to reconstruct, therefore the direction can be only determined within a cone, because one can only determine the scattering angle. So the direction is a cone. Okay, it's a cone. And this instrument is very large, close to 3 meters high, 3 meters, and it's a huge one. COSI, instead, is a small one with better performance. COSI is like this. The material is high purity germanium. This is a very novel material. So we have, for this example, we have 12 pieces of detector. For each one, it's 8 centimeter, and 1.5 centimeter thick. So it's smaller than my palm for one piece. And we put them together to form an array. The incoming photon may hit somewhere here and somewhere there and somewhere there. With this kind of compact configuration, multiple scatterings are very often. Multiple, more than 2 hits. For COMTEL, only 2 hit event. And for this one, we have 3 hits or 4 hits even. Yeah. So the efficiency can be significantly increased with multiple hit tracking. With multiple hit, we have location, and energy. So we reconstruct the event. All right. So that's basic principle of this telescope. And show you some pictures. This is one piece of the detector, and because we have electrodes on both sides in orthogonal directions. Maybe you have a traditional one, traditional pointer.
This is another pointer. 遥控器上的橘色按钮可以用。
Oh, red light works better. that one was also good, but it's green. Red one's good. Okay, so we have electrode in orthogonal directions. Therefore, if there's a hit, then the signal will be collected by these 2 electrodes. So you will know the location in X and Y direction. And then from the time difference of the electric signal, you can infer the location in this thickness direction we call Z direction. Therefore, one can measure the location of the interaction. Okay, and then of course from the first height of the electric signal, you estimate the energy. Okay. Then, see, this is one piece of the detector. You have strip electrodes, and this is the mirror. You see the backside. And again, this is that piece of detector, and I show you here. This is 1 fingers of 1 hand. Okay, so it actually is small. 1 piece, very small. So for this project, these are the partners in this project. And this project, in the past 10 years, it was kind of balloon from stage, because we don't have a satellite and we want to demonstrate the performance of this instrument. So we use NASA's balloon, high altitude balloon. And these are the So it's not really IAA, it's Physics Institute. Maybe I should not point it out. Anyway, all right. So in the past we had several balloon flights from the US. From this one failed, crashed. But I don't have time to tell you those sad stories anyway. And then we also went to Antarctica for a short flight, which was not that successful. And today I will show you some pictures and results of this flight from New Zealand in 2016, because it was a very, very successful one. Look at this duration, 47 days. So the balloon actually circled the Earth 1.5 round. And we also had very good results from this flight. And this year, actually, we plan to have a similar flight, hopefully with a longer duration, but it's cancelled because of COVID-19. Yeah. My students actually flew to New Zealand, stayed there, but somehow our UC Berkeley college couldn't come. And stay there and wait for further information, and then finally NASA decided to cancel that mission. Okay, and then my student then tried. Yeah, at that time it was in March, end March. So try to fly back to Taiwan and then go to 14 days quarantine, blah blah blah. Okay. So it was canceled. So in the following I will talk about this flight, 2016. Okay, so show you some pictures. This is the detector, the array, the germanium array, and put into a cryostat. This cryostat, some cooler, and there is another shielding, and this time we use cesium iodide as a shielding. Detectors are here, cryostat and shielding. Okay. And now you more or less know the things, shieldings, the outer part, and cryostat. And the whole thing we put on top of a gondola to fly with the balloon. So this thing is this small thing. Okay. Yep. All right. So these are pictures that our students working with students from UC Berkeley. This lady now is working in Ghana Space Flight Center, and you see this is the picture in New Zealand 2016. And there, every time when we actually did testing assembly in the lab, UC Berkeley, and then we put them apart, ship them to New Zealand. And to New Zealand, we have to assemble them again and then test them again. Okay, and this is a certain stage of the testing. They call it hand test. In addition to the payload itself, then we have to weigh the whole gondola, and then we also need to check the communication. Okay. Anyway, typically that was 1 or 2 months working. And finally, as you can see here, the gondola is here, and our payload is somewhere here, and the balloon was inflated, and then balloon will be released, going up to somewhere right above the crane, and then this point will be released, and the gondola will go up with the balloon. So basically that's the process. Okay, so it's successful. And then someone took this picture. When the balloon went up to this height, 33.5 kilometer. This is the usual altitude that our payload is working. So someone used a telescope to take this picture. This is the balloon, our gondola. Somewhere here, very tiny. Our gondola is roughly, say, 5 meters dimension. This is about 150 meters. Yeah. And on the ground, as you saw, the balloon was, say, 10 meters large, but when the balloon go up there, it's 150 meters. So nice. Well, it has nothing to do with astronomy. Okay. Then, for that flight, launched from New Zealand, and then it goes this direction, and then passing through South America and then come back. It took only 2 weeks actually for a circle, only 2 weeks. And at that point, NASA people are responsible for the balloon. They say, oh, mission completed, because they want the balloon to go around one circle. Then they say, mission completed. That's only 2 weeks. That's not enough for us. So we actually hope the mission can continue forever. And indeed, yeah, it continued, okay? It continued, and then it spent almost 1 month here in the Pacific Ocean. Yeah, very good, very good. And then around July, early July, the balloon entered South America, this continent. Then NASA decided to cut it off, terminate the mission. Okay,
So,
yes.
Hsiang-Kuang, if we don't stop the balloon, they will fly forever. How long can you
Of course, it will. I believe it will fall down at some point, because the leakage of the gas inside the balloon. But that's a complicated issue. This balloon is so-called super pressure balloon. Usually, one use zero pressure balloon, but zero pressure balloon has a day and night cycle in the altitude. And NASA uses this super pressure balloon try to control the altitude to be stable one. Yeah. But if my student come here to give a report, they will show you detailed information about the altitude variation, and you will see actually this balloon was not that successful. At some point, I believe there was a leakage in the gas. Yeah. Anyway. That's not astronomy, that's only balloon. So, and this is the exposure map. Some result of that flight. So, the most exciting result is that during that flight, COSI actually discovered one GRB and sent out alert. That is the GRB, this one. And this is light curve. This is about 10 seconds. And this image, all sky map, is made with roughly 10-second data. And you see it's very bright there. During that 10 seconds, it's the brightest source in MeV energy range. Okay. And we also, I think, we published a paper to discover this one because we try to determine its polarization. Yeah. But no polarization was measured. So we have upper limit about 50% upper limit polarization degree. And of course, there are other results. This is crack. And this is galactic center at 511 keV. And this is Centaurus A. This is Cygnus X-1. Okay, so these are nice pictures with a lot of massage on the data. Okay. All right, so move on. So COSI, then that was for balloon. And then UC Berkeley team as the lead submit a proposal to NASA. That's for SMEX program. And then as I explained, if everything goes well, it will be launched in 2025. And the orbit is low inclination, and LEO, low inclination, low altitude Earth orbit. Okay, anyway. So for the SMEX project, the collaboration changes a little bit, but I believe you do not really remember all those things. But you can notice from Taiwanese side, only Tsinghua remains, because now it's more complicated, and these big guys all come in, so there's not enough room for us to play around. Okay. Anyway, yeah, but it's good. We are still there. Yeah. All right. So for this satellite, for this space mission, the instrument is similar to the balloon-borne one, very similar. But the only change, two things. This is 4 layers. So now we have 16 pieces of detectors. In our balloon stage, we had only 12. Okay. And another change, the significant change is that the strip the pitch of the strip for this mission now is smaller. For previous one in the balloon stage, the pitch is 2 millimeter. So we have 37 strips on one side. And now the pitch is 0.58 millimeter. So roughly 4 times more strip. So that will of course make the spatial resolution in the detected volume better. Okay. Of course, there are other problems with charge sharing, crosstalk, and so on. Okay. Yeah. But hopefully, this kind of improvement can further enhance our performance. And I don't want to go into details of the performance. So why do I show this picture? Okay, go on. Skip. Okay. So, but one thing I should tell you is that even during the balloon flight stage, the performance, the sensitivity, basically the sensitivity of COSI, although it's an instrument this large, okay, this large, it's already better than Compton. Compton is a huge one. It's already better. The reason to be better is that the background rejection is much more efficient for COSI because of this kind of 3D tracking of multiple scattering. So we can determine very well the direction of the incoming photon. Therefore, we can reject background better. That's the key. And of course, there are other issues. For example, Compton, as you saw, is 2 layers. So if photons scatter to other directions, then it won't be caught, right? And our compact configuration will give us larger acceptance angle. That also helps. Okay. All right.
Sorry.
Yes.
One technical issue.
Yes.
Problem. Is the germanium thickness reduced in the new system, new detector, and the thickness of germanium?
Still the same 1.5 centimeter. 1.5 centimeter in the new system. Thickness is the same. Okay. Yes. All right. So let's move on to the second project that I want to talk about. We will get smaller and smaller. Okay. This project we call Compton Polarimeter. So it's COMPOL. The current status. Okay. This is a short summary. COMPOL is a small Gamma-ray polarimeter to fly on a CubeSat. CubeSat. Later I will say something more about CubeSat. And its science goal is to measure polarization of soft gamma rays from signals as well, from one particular source. That's a Berkeley X-ray binary. Okay. And now, actually, although it's a small one, but the collaboration, in fact, is also quite large. People from Taiwan, from France, from Vietnam, from Germany, and now we are also proposing most ASIAA, that's Taiwanese French bilateral collaboration project. I'm waiting for the result of this funding, and according to information from my French PI, he also submit to ASIAA. I submit our proposal to MOST, and they review separately. And later, MOST and ASIAA will merge their priority list, and then to pick out those projects which have high priority on both sides. According to my French PI, their priority is very low. Anyway, but that's not yet official. Anyway, and then this collaboration is seeking CubeSat opportunities from Taiwan, maybe, also maybe from Vietnam and Europe. That's the status. And what is this instrument? These are pictures. Later we will see this again. Okay, don't worry. And so this is the current coloration. So you see academia silica again. Okay. All right. Signals is one. The purpose of this project is very simple, direct. Signals is one. We want to observe signals is one. And I hope that you more or less know what it is. X-ray binary, high mass X-ray binary. Signals is one as a Berkeley X-ray binary. It switch between so-called soft and high and soft and hot and low state, spectral states. In soft, high and soft state, the spectrum goes like this. And in low and hard state, it goes like this. Okay, so it changes. And of course, as an astrophysicist, the issue is to answer or to describe what is the origin of this emission. What happens in a cartoon like this, or in a accretion disk, and so on. Some rough idea is that the soft component comes from inner disk, accretion disk, from inner disk. And this part, most of people believe they come from Compton photons, which are photons scattered by a certain Compton cloud. So they are inverse Compton scattered and to be a higher energy photon. There are soft photons emitted from disk, and then some goes to the Earth, so we observe that as this component. And this part is photons emitted from the disk but scattered by material here and then go out. So they have higher energy. Okay. But then go to even higher energy. Very often there seems to be another component. It's not that clear. Whether there is another component or not, that was the question. Okay. And so polarization measurement may help. Oh, too much information here. So don't worry. Again, spectrum. Soft part and the middle part, and there's likely another component. You see this is 100 keV, the soft one is below 10 keV, around 10 keV. So it's not clear whether we should use a cutoff, exponential cutoff component plus another power law or not. Okay. So polarization measurement actually can help. For example, in this paper, by the way, Philippe Laurent is my French collaborator. Yeah. They use EPIS on board integral. They measure polarization in different energy bands, for this band, and this band. And they found that in this energy band, the polarization actually is quite low. They did not detect that, so they have an upper limit. And in this band, high energy band, the polarization is quite clear and high. Therefore, from the different polarization characteristics, they conclude that there are two components, and they come from different locations in the system. And very likely, this high energy power law component comes from the jet, so that with synchronous normalization, the polarization degree can be so high. Okay, so this is one example that polarization measurement can really provide us a much more powerful diagnostic tool, okay, to understand the system. But not too long later, there's another paper using SPI. This is another paper on the same sector integral. They also report polarization measurement, blah, 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 for very low energy one, okay, on the upper limit. For this energy band, this is actually similar to this band. One may say they are basically the same. From this instrument, they measure polarization 40% with some error. And with this instrument, its upper limit is only 20%. So there is inconsistency here. Okay? And there are other measurements. So still, some more independent measurement is desired. If you are in this business, then you will understand how unreliable they are. Okay? All right. So now we want to solve this issue. Thickness is one. But certainly we don't have a huge space telescope, right? So we want to use a CubeSat, which is easier to get. But high energy sources emit very few photons. And CubeSat are small, so your detector must be small. What can I do? So looking at one spatial target all the time, I mean 1 year, 2 years, all the time, only one target. If you have a CubeSat, which is not expensive, so you can ask your CubeSat to observe one star all its lifetime. Okay, then you can accumulate a lot of data. That's our idea. So the instrument for this polarimeter is like this. Silicon detectors, maybe with strip electrode, and then we can have some scintillator array at the bottom. So the idea is similar to COSI. The incoming photon hit maybe silicon or maybe scintillator, yeah. And then second hit, third hit, and so on. And we can measure location and energy, so we can reconstruct. Okay. And this thing, our current design is that this is actually very small. From here to here, 5 centimeter. 5 centimeter. Yeah, because we want to put it in a CubeSat. So the idea is that to have a CubeSat like this, 3U CubeSat, and our detector can be here. So you can see this is 5 centimeters, so this is 10 centimeters. Yeah, and with a shear, and we want our CubeSat to rotate around the direction of Cyg X-1 to eliminate some systematic bias. Okay. Anyway, so that's more or less it. So I want to CubeSat. This is a slide for CubeSat. What are CubeSat? You already saw the 3U CubeSat. 3U, by 3U, I mean 3 unit. So satellite, if we classify them by mass, the usual terminology is like this. Large one is more than 1,000 kilograms. Okay. Large one is only Hubble is a large one, GRO, a long time ago GRO. Now, very few space agencies wants to make a large one. A medium size, this one, small satellites like this, smaller than 500 kilograms. And then for smaller ones, there are different names, mini, micro, nano, pico. Yeah. There's no CubeSat. So CubeSat is another thing. CubeSat, somehow, some people on the Earth, yeah, they form a union and then they define some spec. The idea is to have a very standardized spec so that mass production is easy, and the spec is the same. What the user needs to do is only to plug in the user's payload, and then it will work. That's the idea of CubeSat. So, roughly speaking, 1U is 10 centimeter by 10 centimeter by 11.35 centimeter. I don't know why there's a number like this. If you are interested, go check this website. Okay, and typically 1U is about 1 kilogram. So previous 3U thing I mentioned 3U. Okay, the next page we will see again a 3U. That's one example. 3U CubeSat. So from here to here is only 30 centimeters. Okay, and these are different size of CubeSat. You can have a very huge one. This maybe 12U or 20U, yeah, and this may be 2U or 1.5U. And by the way, NSPO is the space agency of Taiwan, will launch 3 CubeSat according to a schedule. Okay, by the end of this year. Now it's October. Yes. Okay. 3 CubeSat. One is 3U. NCU is the one for payload on that CubeSat, and another one is 2U. 2U. The 3U one is called 飞鼠卫星, and the 2U one is called 坚果卫星, and that one is made by 湖北科技大学. And there's another 1.5U called 玉山卫星, made by a commercial company. Okay, they will be launched this year, hopefully. Okay, so this is CubeSat. So, come back to Compol. The previous model I showed you is this one. you probably can imagine silicon sensor and scintillators. And in fact, we also study other models. For example, to have thinner silicon detector, or to have purely scintillator without silicon detector, but have a thinner array. But now we have 2 layers of array, or put it upside down, blah, blah, blah. Or we have 4 layers of array. The gray part is scintillator, and then put some of them upside down. And then we check the performance with all these different kind of design. We check the performance, we check the capability of polarization measurement to see which one is better. Of course, within this kind of restriction, that's why you see this is about 1.2 centimeter. And all these things, the thickness, the sum of the thickness is also about 1.2 centimeter. Because of the weight limitation, we cannot have too heavy and detector. Okay. So we studied performance of all these different models, and I really don't want to show too complicated pictures. Yes. Anyway, the message is that, let's look at this figure only. For this low energy band, different colors means different models. We have 6 models. Okay. And then AIM cut. Forget about AIM cut. Okay, that's too complicated to explain. And the y-axis is MDP. That is minimum detectable polarization. You have a detector, and then you want to know what is the minimum polarization degree in an emission from a source that your detector can measure, right? Okay, so that is MDP. And most of our model, actually, the MDP is like this. This is 10%, 11, 12, 13, 14. So it's around a little bit above, or for these models, they are around 10% MDP. So that means for this energy range, if we go back to here, that is energy range about this one. We will be able to measure polarization if the polarization degree is larger than 10%. So it's possible we can make some contribution here. Okay, and for this energy band, remember this upper limit and this detection. The performance of our detector will be like this is 20%. So if in this energy range, if synchronous one really has a polarization 30-40%, we will be able to measure that. Okay. If we cannot measure it, we may put some upper limit, say, to this range. Then the previous SPI result then will be very questionable. Okay. So you see, our detector is so small, but it can do the job that integral is a huge one. SPI is something like Compton, huge one. But we can check their result. So this CubeSat is very good, right? Okay. But I should say this result is obtained with 10 megasecond on axis oscillation. 10 megasecond, how long is it? 10 megasecond? 100 days only, right? And our CubeSat may lifetime 2 years is possible, 2 years. So in 2 years you have 100 days. You won't observe any other things. So that should be achievable, right? 100 days achievable. Yes.
During the lifetime, signals A can go from high to low, low to high.
Yes.
Will that affect your analysis?
Yes, you are right. You are very right. I don't have time to explain the details. It's possible that we can separate different spectral states to see the different polarization state in different spectral state. It's possible.
Do you need another satellite to tell you whether now it's in high or low?
We can have spectral analysis with our data also. Yeah, so it's possible to do it by ourselves. It's possible. And on the other hand, most of the time it's in half state. Yes.
And indeed, time evolution of the hard or soft state is essential to discriminate the emission process. I mean, for instance, as the accretion rate increases, then the transition radius between ADAC and standard spectroscope comes in,
Yeah.
and then the ADAC component, which consists of inverse contour and Bremse stratum, declines. Then the spectroscope type standardized emission appears from lower energy, then it becomes brighter, and the peak energy becomes higher. So it is essential to observe the time evolution of the spectrum state.
Yes, that's also a good point. But as you can see, Koichi is a theorist. Yes, but yes, yes, yes.
So it's
Yeah.
very
Yeah,
essential
yeah.
to observe
The evolution of the spectral evolution. Yes, that's very good information. Yes, we can do that. We can do that. Although, yeah, we can try to do that. All right. So then that's it. Therefore, another summary is that after our study, that it's achievable. It's achievable with a small instrument. We can achieve that scientific goal. And we have these two models grow better, and a prototype will soon be built if we have the money. And I didn't put if we have the money. Okay, we are looking about CubeSat. Yeah. All right. So because I'm running out of my time, this is the most important project I want to talk about today. Yeah. The Gamma-ray Transient Monitor project. And the current status. Okay, short description. This GTM is a suite of small gamma detectors that you will see, similar to COSI, but thinner than that. It's already selected to fly on Formosat 8, the second one. B is the second. According to NSPO schedule, the first one, Formosat 8A, will be launched in 2023, and the second one, 24, if it's not delayed. Okay. So the science goal is to monitor GRB. Yeah. And it's also possible to detect bright transient from other sources like megaton burst or giant flares. It can also detect. And also a lunar orbit GTM, so we call it LGTM, was also selected by NSPO, lunar orbit. Formosat is in Earth orbit, and lunar orbit set for feasibility study. So if NSPO really want to launch a spacecraft to orbit the moon, then we will have our GTM on board. That will be very good. But there are some uncertainties whether NSPO really wants to go to the moon or not. Yeah. Yeah. All right. If it comes true, it will be the first GRB monitor in the lunar orbit. First for humankind. Okay, of course. Yeah. First. Yes.
What is the advantage?
Go to the moon. Yeah. Good point. Basically, two. One is that in the lunar orbit, the radiation background is much weaker than in Earth orbit. Because Earth orbit, because of atmosphere, albedo background is very strong. So lower background, then your instrument will be more sensitive than in Earth orbit. That's one. And the second one is that in lunar orbit, if you have one in Earth orbit, another one in lunar orbit, if these two detect one GRB, you have much better capability in localization using time difference. Much better. Yeah. Currently, people only use satellite around the Earth, so the baseline is too short. Yeah. Okay. So it will provide very good localization capability. That's the most important one. Therefore, okay, that's good one. So I like this very much. Yeah. All right. And the PI is me, and co-PI is this one, Lin Zhixun. This is why you always see this. Now you see the reason. Yeah. Okay, and Cao Zizhi from power mechanical engineering department. All right. So because I don't really have time, so I will skip the science justification because you know they are already GRB monitors. Why bother to have one more or two more? Okay. So this slide, just with some argument, just want to show that we do appreciate if we can have more monitors. Yeah. So I will skip it. I'll skip it. But basically, I would say, you know, the sky coverage, for example, of Fermi GBM, which is the major one, and also Swift. Fermi GBM, of course, is an all sky monitor, but the Earth will block almost half of the sky. Okay. Swift has a field of view only say 50 degree, 60 degree wide. So there are a lot of missed GRBs. In those slides I skipped, one can see some very likely example. Yeah. There are some gravitational wave events which are believed to be neutron star merger, but without electromagnetic counterpart. The event in 2017 was the first one, so far the only one. You know that event? Like, I hope so. Okay, anyway, so come to our design. This is Formosat 8. And we will put our detector on one side and on the other side. And so that we can monitor basically all sky, except for that part occluded by the Earth. We have one here and another one on the back. And this one is only 10 centimeters, means 10 centimeter. You may wonder why it should be so small. I don't want it to be so small, but that's the volume allowed by NSPO. The main payload of this satellite is this one. It's a remote sensing one. You know, the earlier name was Rockset. Okay. Anyway, number 2, Formosat 2 and Formosat 5 now is working. They are all remote sensing one to map Taiwan for many very good purposes. And this is the same, but with hopefully better resolution. Okay. So this is the main payload, and we are only allowed to have this volume and total weight 2 kilogram. Total weight 2 kilogram, and power 1.8 watts orbital average. Okay, so we have to work under this kind of restriction. So we have 2 modules, and one module is like this. And as you may guess, this is the detector, one piece of detector, another piece, and another piece on the bottom. So there are 4 pieces of detectors in one module. So with these 4, then we can monitor this part of sky with another one, monitor another part of sky, and with the flux ratio, if we have a certain event coming from a direction, so you can expect these detectors will have different flux, right? Because different direction. So with the flux ratio, we will be able to determine the direction of the GRB. This principle actually was used by Berkeley, Compton CGRO, and also used by Fermi GBM. The same idea. Okay, and for one module, now you see 4 detectors, and this is the effective area. Okay, and you see again the module, and if you open it up, 4 detectors, and of course, okay, scintillator again. We use scintillator, some material, GHG, blah blah, and use SIPM. It's thin and low power consumption, and light. Okay, and there's a PCB. So you put this one as one piece of detector. So this is one piece of detector, and you have 4 pieces, and another board here to collect all the signals. Okay. So with such a small instrument, how many GRBs do we expect to observe per year? It's so small. So this is Fermi GBM. distribution, fluence distribution of GRB, 10 years, 10 years. And this is short GRB, this is long GRB, okay? Then we simulate with our instrument with low Earth orbit radiation background. We assume a polar orbit, which will be the orbit used by Formosat 8. And we put in the radiation background so we can estimate our sensitivity to how dim a GRB we can see. And of course, we need to assume some spectral shape of GRB and so on. So of course, we use sort of typical one, or that we have this knowledge from previous studies like GPM or Conus wind. Therefore, the answer is that for short GRB, our 3 sigma or 4 sigma detection limit will be here for short GRB. For long GRB, it will be here. So the number here it probably is difficult for you to read. This is 70 roughly, and this is 1200. But this is 10 years. This is 10 years. Therefore, 1200 translate into 120 per year. 120 per year. We are able to observe this kind of GRB brighter ones, 120 per year. But for Formosat 8, the duty cycle allowed for scientific paper to work is only 1/3. I don't know for what reason. Yeah. So we need to cut the number down to 40. So still 40 GRB per year. That's a lot. That's nearly 1 per week. That's already a nice one, right? And then if we have LGTM, which I hope the duty cycle is 100%, yeah, then we'll detect more than because of lower background. I haven't simulated lunar background, but with Earth orbit background, the number is 120. So it should be more than 120 per year. So that means 3 days, that once per 3 days, roughly. So we will be very busy, right? So that's more or less, you see, that's a new era for Taiwan's space program. This is really first space telescope in Taiwan's space program, right? Thank you very much.
Any question about Hsiang-Kuang?
About my talk,
Yeah.
not about me.
So for the COSI and the
Compton and GPM.
which part is the strong for Taiwanese group? Which component or?
Oh, for GPM, as you can see from the collaboration, basically it's Lin Zhixun, and Cao Zheshi, and me.
Yeah, that part.
We make it 100%.
Yeah.
And for Compton, we are able to take care of it 100%. We are able to, but we have French collaborators, so we try to maybe second detector can be provided by French group, second detector. But in fact, we are able to cover 100%. For COSI, we are not able. For COSI, in the balloon flight stage, all the electronics were made by Taiwanese team. Yeah, in the COSI balloon flight stage. And of course, we contribute manpower for the balloon campaign and data analysis, data pipeline, this kind of thing. So basically that's electronics. Germanium detector is difficult. The crystal can be bought from some company. There are 2 companies on the earth, but I heard that there are more and more. Even some university can make it very high purity. The degree of purity is the key for the detector to be useful. Okay, so that can be purchased, but the surface processing to make those electrodes, that's some skill. And for COSI project, it was done by Berkeley National Lab. Yeah. So that part is difficult. Yeah. So we are not able to really handle that.
Good. Any other questions?
Can you need data?
Could you say again?
GTM
GTM.
provide
Yeah.
light travel data.
Light travel.
Light travel.
Light curve, yes. Yes. You mean if we detect some GRBs?
No, I mean
Oh,
laser.
Blazer. It depends. Blazer. I have to check how bright the non-blazers are. My quick answer would be no. My quick answer would be no because they are not that bright. But I will go check. Yeah, and also because GTM, the localization capability is based on the time variability, transient. If it is a steady source, then it's probably impossible to distinguish. But blazar varies. Yes, blazar varies, particularly when they emit neutrinos. Yes. But the time scale is actually different. Then I don't know, maybe it's not that easy.
Blazer spectrum gives higher energies than MEV.
Yeah, MEV, yeah, that's another point. Yeah, MEV blazars are deep. Yes. Yeah.
Any other final question?
So you mentioned about the duty cycle, one per
1 second.
is that restricted to daytime or nighttime?
I don't really know. NSPO say 36%. I don't really know the reason. And because science payload is the secondary payload there. So the major mission is remote sensing. Yeah. I'm not sure whether they want to say power or bandwidth or I don't know. Yeah. Maybe later I can ask simply because of curiosity. I can ask. Yeah. Actually, I want to ask them to allow GTM to operate all the time. Yeah, so I have to ask. Yeah. Now, because we are now awarded this opportunity and some funding, so we need to discuss with NSPO very frequently. Yeah. They also want to control our progress. Yeah. So that we can deliver on time. Yeah.
Okay, time's up. Let's thank Hsiang-Kuang again.
Thank you.